Hi students, it's Mr. Bornheimer and this is section A of our physics notes. So why don't we begin? When we first introduced this section, we introduced it with a question, and that question was, what is force? A force is something that acts on an object. We are familiar with many forces in nature, some of them natural, like the force of gravity and whatnot. But the simple definition of a force is that it's a push or pull on an object. Now, most forces in nature require a very simple kind of rule, and that is that you must have two or more objects interacting. So if there was one, let's say, object in the whole universe, there would be no force because there would be nothing for it to interact with. When I push on something, it's me pushing on another object, a second object. And if I pull on something, it's me pulling on a second object. When the Earth exerts gravity, it's the Earth exerting gravity on something. So forces always come in pairs. That's a key idea here, that there are pairs involved. And those pairs are called interaction pairs, force pairs. So a force always comes with the stipulation that it must include two or more objects. Now, when we look at an object, we might say that the force of gravity is being exerted on me. Well, that must mean that something is causing that gravity. Now, that seems like a very simple answer. The answer to that particular question would be that it's the Earth. So something that creates a force, something that exerts a force on another object, is called an agent. And there are several different types of forces that we refer to as being agents or having agents. A couple of things here that I would want to address would be this idea that there are forces that either are in contact with something. We call these contact forces. So I'm pushing or pulling on an actual, not contacting, that I'm actually pushing or pulling on an object physically through contact. This would be, for instance, any air resistance would be an example of this. Air resistance is where air is physically coming in contact with an object. Friction, okay, would be another example of a contact force. Friction is something that interacts between two objects, and it's only due if they are interacting via touch. So basically, touch is what we see with contact forces. Then there are also field forces, and yes, I'm actually talking sort of like force fields, though not the kind that protect ships from photon blasters, but force fields would be things like the gravitational force. Okay, so gravity causes a force field. Gravity can exert itself on an object without actually being in contact with that object. Hence the reason if I jump off the Earth, gravity pulls me back to Earth. Okay, and then there's another one, and it's electromagnetic fields. Electromagnetic, things like magnets or electric fields that cause a charge. And this actually happens in transformers. So we see things like field forces and contact forces. Now, there are four fundamental forces that occur in nature that account for all of the bonds and things that we have, chemical bonds, what holds the Earth together, how planets stay in orbit. And the four fundamental forces include gravity, which we've already named, okay, and electromagnetism. And then the two that we really don't talk about in this class so much are strong and weak nuclear forces. So these are the four fundamental forces that occur naturally: gravity, electromagnetism, and strong and weak nuclear forces. All right, so if you think on a daily basis, what might be an action-reaction pair? Okay, when we say action-reaction, when you push on something, something happens. When you pull on something, something happens. So what is an action-reaction situation? A common example might be, you open a door. So you push a door, and the door opens. Okay, you could pull on a door and the door could close. All right, so all of these ideas of force, pushes and pulls and natural forces and contact forces and field forces, they are important, but in order to really understand a lot of the situations we're going to be looking at, we're going to have to be able to diagram. One of the main diagrams that we're going to be looking at is the idea of a free body diagram. Okay, so imagine for a moment that you have a table, and on this table is a book. Okay, now think about a book sitting at rest on a table. Okay, it's at rest, so the velocity of the book is 0 meters per second. And we have to ask ourselves, what forces are acting on the book? Well, we know that gravity acts on all objects, so there must be a force due to gravity that's acting on this object. We call this force F sub g, means the force due to gravity. So I'm going to kind of put that up here, make a list. Okay, force due to gravity. But if that was the only force, then that book would be going towards the earth. There'd be nothing to balance it out. There'd be no push or pull to balance it. So a force of gravity is pulling down on the book and there's nothing to balance it out, it's going to move down. However, it doesn't, because there is a force that's opposing it. Hence the reason that it's sitting at rest on the table. And this force would be the force of the table on the book. So the force of the table, so T on B, table on the book. Okay? Now, notice that these two forces cancel each other out. And when they cancel each other out, there's something special. We would say that the F net, or the net force, total force, after you analyze everything, acting on the object, is 0. Okay? So this object isn't moving because all the forces are acting on it are 0. Now, what if we were going to talk about all the forces acting on it? Gravity, like some forces act on it and we don't even realize it. Like Jupiter is acting on the book. There's gravity of Jupiter. It's weak at this distance, but it's still there. Gravity of the sun, air. What about a tiny little wisp of air in the room? Or maybe there's a little bit of metal in the book from the binding, and that's being attracted to the North Pole of the Earth. Okay, so there's all of these forces, and we have to isolate them. We have to really look and say, what are the forces that are significant? To do this, we have to define something called a system, and that means that we isolate a single object with which to analyze. Okay, normally we put a dotted line around it. So in this case, we put a dotted line around the book. It's the system that we're trying to analyze. So this system is important. And we normally only look at those forces that are significant, ones that are not so small that they're negligible, like the gravity of Jupiter at this distance, and so on and so forth. So the main forces would be the force of Earth's gravity and the force of the table on the book, because it's resisting it, equal and opposite. We would call these two, by the way, action-reaction pairs. Gravity pulls down, table pushes back. Okay, another example of number 5. But this diagram is kind of messy. And oftentimes, just like when we were looking at motion diagrams and particle models, we want to be able to simplify a diagram. We want to be able to make it so that we don't have all this extraneous objects. And some of you are not comfortable drawing, so we want to make it as simple as possible. So what we do is we take the object and we make it a single dot. And we say, what are all the forces acting on that dot? Well, that dot represents the book, our system, and we say, well, there's the force of gravity. Oops. There's the force of gravity, and then there is the force of table on book. And that's it. This right here is called a free body diagram. And it means that we've gotten rid of all of the extraneous, things like the edges of the book and the table and the ground, and we're looking at just our system, the object that we're analyzing. Free body diagrams are going to be something we're going to look at a lot, so it's important that we really take the time to look at them. There are other examples of free body diagrams. If you're curious about those or you're confused by this idea, please come see me. Okay. So in order to mathematically analyze force, we really have to take a look at, okay, what is a force? Well, first of all, we know force is a push or pull. Okay, great, but it's a push or pull on what? Well, it could be anything, except it has to be something. And that's not meant to be a trick question, but it's true. If it's something, it means that it must have mass. Okay, so there is something in this that we have to say, okay, it involves mass. And if we push or pull on an object that has mass, then we're changing its velocity. We say we have a mass sitting on the floor, or you could say even we have this cup. Awesome cup. Let's say the cup is at rest. And let's say that I go to push on the cup, I push on the cup, and it moves. Well, by pushing on the cup, I've changed the velocity of the object. It was at 0, and now it's something greater than 0. So I've changed the velocity, and I did so in a time interval. So if I changed velocity in a time interval, that is, in essence, the definition of acceleration. So I have a push or a pull, or a force, acting on a mass, and when I do that, it accelerates the object. So there is a relationship here, some relationship between force, mass, and acceleration. Okay? So that being said, we have to look at kind of what Newton looked at when he first looked at force, mass, and acceleration. And we say, okay, Newton looked at acceleration, and he looked at it in relation to force, and he looked at it in relation to mass. Okay, so we said, okay, how do these two things, force and acceleration, compare? Let's think about it. Let's say we have this remote, and it has a constant mass, and I'm going to apply a force and accelerate it. Okay? Well, now let's say that I apply a larger force and accelerate it. So I push it way over. The larger the force, the greater I'll change its velocity, so the greater the acceleration. We would say then that if force goes up, acceleration must also go up. This is known as a direct proportion. However, now let's say that the force is constant. I'm going to push on this object every time exactly the same. And I'm going to see what happens when I do different things. So I'm going to push on this object. Okay, I pushed on it, I moved it, I accelerated it. Now let's pick a much more massive object. Let's say I'm going to push on this wall with the same force. So I go to push on the wall. Well, the wall doesn't really accelerate. It doesn't accelerate because it has so much more mass. Okay, same is true if I push on this object and I push it across my hand, okay, and then I push with the same force on this pen, well, the pen's going to accelerate much faster because it has less mass. So if I increase acceleration, or excuse me, if I increase mass, the more massive the object, the slower it will accelerate, the harder it is to accelerate the object, so acceleration goes down. If I increase mass, however, or excuse me, if I decrease mass, I make the object very, very light in essence, then it'll be much easier to accelerate that object, and the acceleration of that object under the same force will be much greater. Notice the arrows are opposite. This is known as an indirect proportion, and it is written like this. It means as one goes up, the other goes down. Unlike our acceleration and force proportion, which is the direct proportion, this one goes up, this one goes up. Acceleration goes down, force goes down. The opposite's true here. If acceleration goes up, mass must go down. And if mass goes up, acceleration must go down. This is an indirect proportion. Now Newton looked at these two relationships and he said, hey, let's combine them. So he said, well, if this is direct, then F would go on the top, mass could stay in the denominator, and we end up with something that looks like this, which is really interesting. This is a proportion that involves all three variables. Acceleration is directly proportional to force over mass. And what we see happen is that this actually turns into the equation, acceleration is equal to F net over mass. And this is known as Newton's second law. And so what we want to do is we want to go ahead, whoops, I don't want to move that. We'll just rewrite it. Newton's second law is acceleration is equal to force, net, that's important, over mass. Or we can rearrange it and say that F net equals ma. And this is known as Newton's second law. Okay. Now, one of the things I'd want you to try, and I had the class try on their own, is I want you to think through what happens if we manipulate the variables in F net equals ma. Or you can look at the equation A equals F over m. What happens when you manipulate these things? This is a really good exercise, and I want you to try it on your own, and then you can, post your answers either on this, video or send me an email. One of the things that I find is that it's probably easier to look at this equation here, and this is an important concept, being able to manipulate an algebraic expression by looking at changes in the variables. There are some questions on your test that refer to this concept. Lastly, we want to know what units does force have? Well, force is equal to mass times acceleration. Mass, in this case, has units of kilograms, and when you multiply it by acceleration, meters per second squared, you get this. Scientists thought, well, this is kind of messy, let's simplify it, and so they assign this kilograms times meters over second squared, they assign this the letter N, or the Newton, which is the units for force. This ends section A of our notes. If you have any questions, you can email me or go to my website, bclassroom.com, and post your questions in the contact form on that page. Thank you for watching and have a wonderful afternoon.